Swayam Prabha. Digital India. Educated India.
Very good afternoon. I welcome you all to the session of Thermal Engineering Basic and Applied, and the topic of our today's discussion is gas compressor and optimum pressure ratio. In the last class we have discussed about gas turbine units, and to analyze the performance of gas turbine units we had tried to represent the processes those constitute together to form a cycle using an air standard cycle, that is the Brayton cycle. And we had seen that in a gas turbine unit, whether the unit is based on open cycle or closed cycle, compressor is an important part, and the rise in pressure of the working fluid which is performed by a compressor is very important to dictate the overall efficiency of the cycle. So, today we shall discuss about the gas compressor, but before going to discuss about gas compressor, let us first focus on an important term that is called optimum pressure ratio. So, if we try to recall the cycle efficiency that we could establish in the last class, that is 1 minus T4 minus T1 divided by T3 minus T2. This we could write in terms of pressure ratio, that is Rp power gamma minus 1 by gamma, where Rp is the pressure ratio. So, this is what we could write in the last class. So, if we try to draw the TS diagram, then the processes, if we represent here, then this is 1, 2, 3, 4. So, 1, 2 is the compression process, then 2 to 3 is constant pressure heating. So, basically P equal to constant for this process and P equal to constant for this process, that is 2 to 3 and 4 to 1. And we could represent the efficiency, cycle efficiency by defining a term that is called pressure ratio, and this Rp is the pressure ratio that equal to P2 by P1. So, basically you can see the rise in pressure of the working fluid by this compression process, that is pressure rise from P1 to P2. So, ratio of these two pressures is known as compression ratio. So, now if we increase Rp, then we can see from this particular expression, which is very trivial to understand, that if we increase pressure ratio, cycle efficiency will increase, and if we keep on increasing pressure ratio, if it is possible at all, then perhaps the cycle efficiency of the Brayton cycle also can be compared to the efficiency of the Carnot cycle. So, that means if Rp increases, then eta cycle will increase, right. So, what would be the Rp you know for which this eta cycle will approach eta Carnot. So, that means if we keep on increasing pressure ratio, there will be a pressure ratio for which the cycle efficiency will certainly approach the Carnot efficiency. And what would be that? So, you know that if we again draw the TS diagram for the Carnot cycle. So, this is 1, 2, 3, 4. What is the Carnot efficiency? Equal to 1 minus T1 divided by T2, that is the 1 minus T min divided by T max. So, this is the Carnot efficiency. That means, if we now compare the cycle efficiency of the Breton cycle, what we can do? If we increase the pressure ratio, then certainly P2 will increase, and this process in a way is attempting to increase the mean temperature of heat addition 2 to 3, that is the constant pressure heat addition, and that is basically mimicking the combustion process. So, if we increase Rp, in a way we are trying to increase the mean temperature of heat addition, and also an increase in Rp will result in a decrease in the mean temperature of heat reduction. So, what we can do, if mean temperature of heat addition, so that is Tmi, and if mean temperature of heat rejection is Tmo. So, if this is the case, then what we can do? We can write this eta cycle will be equal to 1 minus T3 divided by T1, right, 1 minus T1 by T3, 1 minus T1 by T3, right. So, that is 1 minus T min by T max. So, that means by increasing the pressure ratio, we are trying to increase the mean temperature of heat addition as if T2 equal to T3, and we are also trying to reduce the mean temperature of heat rejection, that means T4 equal to T1. So, then this is the efficiency, that is 1 minus T min by T max, right. So, that is the mean temperature of heat rejection and heat addition, and that would be cycle efficiency, and this cycle efficiency will be maximum if we can increase the Rp, and then it should be Rp max gamma minus 1 upon gamma, right. So, basically what we are trying to do? We are trying to increase the Rp. When Rp will be Rp max, we can go up to Rp max, then cycle efficiency will be certainly maximum, and that would be as if we are we are assuming that at that Rp max cycle efficiency is equal to the Carnot efficiency, and that is we are increasing the mean temperature of heat rejection from T4 minus T1 to T1, and mean temperature of heat addition from T2 to T2 minus T3, that is T3. So, essentially this is the expression. Now, then what we can write from this? Then we can write Rp maximum equal to T max by T min power gamma by gamma minus 1, that is equal to T3 by T1 power gamma by gamma minus 1. So, this is what we can write from this. Now, question is, if we try to plot, so if we consider RP here, if it is eta cycle, then say this is the Carnot efficiency, and if we look at this particular expression when RP max equal to 1, then efficiency will be equal to 0, and when RP max will be RP max only, then efficiency will be maximum, and that efficiency we are assuming that would be equal to Carnot efficiency. So, this efficiency, so this is say RP max. So, this is RP max, and this efficiency is eta cycle max, and that is equal to Carnot efficiency you are assuming. So, what we can see from here is that with increasing RP max, so this is RP equal to 1. So, if we go up to RP max, then efficiency, cycle efficiency will increase. Now, question is, it is really difficult to achieve the Breton cycle efficiency which should be equal to Carnot efficiency, because Carnot cycle is one of the most important ideal cycle. So, next objective should be, it is not possible to get RP max. So, what would be the optimum value of pressure ratio for which the cycle efficiency will be maximum? So, this is basically a theoretical efficiency that we are assuming to achieve by the compression by this compression process, then expansion process, that is the cycle efficiency, but it will not be the case. So, now next objective should be, what would be RP optimum for which cycle efficiency would be equal to eta cycle maximum. So, next objective should be to look at the expression of RP for which cycle efficiency will be maximum. So, let us now work on this particular aspect. So, what is W net and what is Q in. So, Q in equal to Cp into T3 minus T2 and W net equal to Cp into T4 minus T1. If we go back to this, so basically T3 minus T4 minus Cp into T1 minus T2. So, that is if I write here in one step, then we can write. So, this is T3 minus T4 minus Cp into that is T2 minus T1. So, that means we can write Cp into, so that is Cp into T3 minus T2 minus T4 plus T1. So, this is basically the W net. So, now for a given heat input, that is certainly the addition of energy to the cycle through the combustion process, we are getting, that is W net. So, now can we figure out what would be the value of RP optimum for which this W net would be maximum? If W net is maximum, that now eta cycle equal to W net by Q in. So, for a given heat input, what would be the pressure ratio for which we can maximize the W net, if we can ensure that cycle efficiency will be maximum. So, that means for eta cycle maximum, W net would be W net maximum. So, now let us do here. So, W net equal to Cp into T3 minus T2 minus T4 plus T1. Now, we know if we go back to the slide, 1 to 2 and 3 to 4, these two processes are reversible adiabatic processes. Reversible adiabatic compression 1 to 2 and 3 to 4 is reversible adiabatic expansion. So, now we have also discussed in the last class that these two processes can be represented by PV power gamma equal to constant and gamma equal to Cp by Cv, and we can get the change or the property at the exit of the compression and at the exit of the expansion using air standard equation, ideal gas. So, now what we can write here? We can write T2 by T1 equal to P2 by P1 power gamma minus 1 upon gamma equal to, what is P2? If we go back to the previous slide, P2 equal to P3 and P1 equal to P4, because these two pressures are constant. So, this is P constant, this also P constant, that already I have written P equal to constant here. So, what we can write here, that is P3 by P4 power gamma minus 1 upon gamma equal to T3 by T4. Now, so this P2 by P1 and P3 by P4. So, if I write here, this quantity is also Rp, this quantity is also Rp. So, that means what we can do here, we can write Cp into T3, T3 equal to, I can write T3 minus what is T2, that is T1 into Rp power gamma minus 1 upon gamma, and this T3, T4 equal to T3 into Rp power minus gamma minus 1 upon gamma plus T1. Why we are doing so? Because you know that T3 and T1, these two are basically, so basically what we can do here, you know that state point 1 is fixed, and for a given T3 also, T3 that is after combustion, if you would like to apply same fuel, same amount of fuel, then certainly we can fix that T3 would be fixed. T3 will increase provided we are trying to increase T3 by having optimum pressure ratio, but as I said you that I will be discussing today, particularly for this cycle, the compression process is not only to rise the pressure of the working fluid, but also to increase the temperature as well. So, but also to increase temperature. So, what we can do here, we can fix T3 and T1, and that is why we have replaced here T2 and T4 in terms of T1 and T3. So, now question is, we could write the expression of W net in terms of Rp, right, you can see from here. So, what we can do, we can calculate Rp optimum, for which dW net by dRp would be equal to 0. So, if we need to obtain Rp optimum, for which W net would be maximum, because if W net is maximum, then only cycle efficiency will be maximum, and to get it, if we make it dW net by dRp equal to 0, then from this particular expression we can figure out Rp optimum, the expression of Rp optimum, and this Rp optimum should be T3 by T1 power, because you can understand that T1, T3 we could express T2 and T4 in terms of T1 and T3. As I said few minutes back, that T1 is constant and we are assuming that we are supplying equal amount of fuel and same fuel. So, we can also fix T3. So, now for a given T1 and T3, we are trying to get the optimum value of Rp, and that is T3 by T1 power gamma by 2 into gamma minus 1. So, this is the optimum value of pressure ratio for which cycle efficiency will be maximum. Now, if we write here that Rp optimum equal to T3 by T1 power gamma by 2 into gamma minus 1, right. T3 is equal to T max and T1 is equal to T min in the cycle equal to gamma by 2 into gamma minus 1. T max by T min, if we go back, so this is Rp max is also T max by T min power gamma by gamma minus 1, right. So, basically what we can do here, this is Rp max power half, that means Rp max equal to Rp optimum square. That means optimum value of Rp should be root of Rp maximum. So, this is very important that we cannot really get Rp maximum, because otherwise efficiency would be equal to Carnot efficiency. So, that is basically idealized situation, but what we can get, we can really get an optimum value of Rp for a given T1 and T3, and for that cycle efficiency will be maximum. So, now question is this Rp optimum or Rp optimum equal to Rp max under root, right. Now, question is, if we try to place or if we try to plug in the value of Rp optimum in this expression W net and also in the expression of cycle efficiency, let us see what would be the cycle expression of cycle efficiency and W net in terms of T max and T min. So, cycle efficiency for optimum Rp, that equal to 1 minus 1 upon Rp optimum gamma minus 1 upon gamma. So, that means 1 minus what is Rp optimum? Rp optimum equal to root of Rp max, and Rp max equal to T max by T min power, that already we have written Rp max equal to T max by T min power gamma by gamma minus 1. Okay. So, what we can write here? We can write that is T max by T min. So, Rp optimum is Rp max half. So, that is gamma by gamma minus 1 into gamma minus 1 divided by gamma under root. So, that means we are getting that is root T min divided by T max. So, this is the expression of cycle efficiency. So, this is eta cycle at Rp optimum. So, this is the expression of cycle efficiency at the optimum value of Rp, 1 minus root T min by root T max. So, if we know the maximum and minimum temperature of the working fluid in the cycle, we can get what would be the maximum efficiency for that cycle, because that would be the maximum efficiency, because the that is obtained at a optimum value of Rp. Similarly, what would be W net at Rp optimum? As such, this is basically I should say, so this is W net maximum for the cycle. W net maximum that we could write in one of the previous slides is basically the Carnot efficiency that is not achievable in practice. So, this is basically the W net maximum corresponding to optimum value of Rp, and if that is the case, so what we can get here, this is the expression. So, if we write Cp into T3 minus T1 Rp power gamma minus 1 upon gamma, then T4 that is T4 is T3 into Rp minus gamma minus 1 upon gamma plus T1. So, this is the expression, let me verify it once again, minus T3 into this. So, what if we plug in the value of Rp optimum over here, because Rp it should be now optimum, and Rp optimum that equal to T max by T min, right, into gamma by 2 into gamma minus 1, because T max by T min power gamma by gamma minus 1, that is Rp max, under root of that is Rp optimum. So, if we plug in the value of this expression over here, then we can write that is Cp into T3 minus so basically this is what is T max. So, this is as good as T3 by T1 power gamma by 2 into gamma minus 1, because T max is T3, T max equal to T3 and T min equal to T1 for the cycle. So, if we write this, then what we will be getting? We will be getting T3 minus T1 into under root T3 by under root T1 minus T3, it would be minus T3 into under root T1 by under root T3 plus T1, and you can understand that it should be so it should be Cp into root T3 square minus 2 root 23 into root T1 plus root T1 whole square. So, that means we can write in the next slide that W net maximum or W net at Rp optimum equal to Cp into root 23 minus root T1 whole square, that equal to, we can write in a more generalized form, that is T max minus root T min whole square. So, this is the efficiency, that the maximum efficiency corresponding to the optimum value of pressure ratio. So, I should say this is the expression of the maximum efficiency obtainable from a gas power cycle, or this is the efficiency corresponding to optimum value of pressure ratio, that is under root T max minus root T min whole square. Okay. So, with this, if we try to draw the variation of W net, so this is W net. So, you know that if we consider this is the W net maximum, so this is W net maximum, and then we can plot it that when Rp equal to 1 and say this is Rp equal to Rp max, right. So, when Rp equal to Rp max, so this is So, this is RP optimum, right. So, what we can see that when RP is equal to optimum, we will be getting the maximum value of W net, right, because if we go back to the previous slide, this if it is RP max, then this when RP is equal to RP optimum, we will be getting maximum W net. So, efficiency will be maximum, right. So, this is the variation of W net versus RP. So, with this now we can start our discussion on the compression or gas compressor, to be precise, compression process or the gas compressor. So, what we have understood from the discussion that we had until now, that pressure ratio plays an important role and that pressure is developed, that pressure is increased, pressure of the working fluid by an air compressor or gas compressor, to be precise, if the working fluid is not the air. So, what we can discuss now, that compressor plays an important role on the overall cycle efficiency, and typically we had seen that compressor is consuming work from the turbine and it consumes a significant part of this turbine work output. So, today we shall now see the working principle of a compressor and then what are the different efficiencies of the compressor. What is compressor? A compressor is again a mechanical device in which work is done on the working fluid essentially to increase its pressure with an appreciable rise in the density. So, let me tell you once again, compressor is a mechanical device in which work is done on the working fluid. If the working fluid is air, then work is done on the air. If the working fluid is gas, then work is done on the gas with an appreciable rise in density, but the main purpose is to increase the pressure. We had seen that temperature of the working fluid also increases because of this compression process, but certainly the rise in temperature of the working fluid is little as compared to the rise in pressure. So, there are basically two different types of compressor. One is positive displacement type, example is reciprocating compressor. Another type is basically that turbine type, that is rotodynamic. So, examples are centrifugal compressor, rotary compressor, right. So, these two are two different types of compressors. So, positive displacement type and the turbine type, that is rotodynamic, whirling motion will be there. So, rotating part will be there. We had seen, perhaps you have studied in fluid machines course, compressor is also a fluid machine, where the fluid is either air or any other gas. So, in the hydraulic machines, perhaps you have studied that pump, there are different types of pumps available, positive displacement type and also rotodynamic pumps. Similar to that classification, here you also can classify compressors into two broad categories. The first category is positive displacement type, in which the main purpose is to increase the pressure significantly, reciprocating compressor, and turbine type, that is axial flow type, that is centrifugal compressor, rotary compressor. So, basically that rotating components will be there. As I said you that the sole purpose of this particular component, or the sole purpose of integrating this particular component in the gas turbine unit is to compress the air, and the objective is to increase the pressure with an appreciable change in density. Certainly temperature may or may not increase. Now, in most of the cases temperature also increases, but the rise in temperature is very little as compared to the rise in pressure. So, when the requirement of the compressor is to prompt supply of, or we need to supply the working fluid which will be having high pressure, prompt supply of that working fluid, say for example in a combustion chamber or in an IC engine. In that case, rise in pressure together with a little rise in temperature is important, right. But there are other areas in which what we need to do, we need to certainly increase the pressure of the working fluid, and that compressed gas or compressed air will be kept in a cylinder or in a container for a while, and that compressed air or gas which is having high pressure will be used later when need arises. Now, when the compressed air or compressed gas is kept or stored in a cylinder, it is very likely that though a little increase in temperature will be, temperature of air will be there, but that rise in temperature will be certainly increase the temperature of the gas, but the gas temperature will be reduced because the compressed air will be kept in a cylinder. So, basically there are two different applications. In one application, compressed air is promptly supplied to a combustion chamber, or that compressed gas is needed for an IC engine. In that case, a rise in pressure together with a rise in temperature is okay, because we also need to get some more energy. So, basically the compressed air when will be supplied to the combustion chamber, if that air stream or gas stream is having little more energy in terms of enthalpy, that would be good for the combustion process. On the other hand, there are applications in which compressed air or compressed gas will be kept or stored in a cylinder, and that high pressure gas or air will be used later as and when need arises. In that case, rise in temperature is not that much important. So, now question is, if we discuss the compressor, so what we can see from the schematic depiction that we had drawn in the last class, that if we assume that this is the compressor and we are supplying air or gas, and then this is state point 2 and say this is state point 1, and so this is compressor. And we had seen that we need to supply work. So, basically if we consider that convention wise that you have studied in thermodynamics, this is Q and this is W. So, we are following the nomenclature that heat added to the system is positive and work which is extracted from the system is positive. So, this is W and this is Q and this is the working fluid. So, if we apply steady flow energy equation, and we can write that H1 plus Q, or I should say I can write here del cube and del W. So, del cube equal to, or in that case let me write here that is specific. So, if I write here that del Q and del W, so del Q equal to H2 plus del W. So, now we have assumed that the process is reversible adiabatic. So, the compression process is reversible adiabatic, right. Compression process is reversible adiabatic. So, if it is an adiabatic process, so we are not allowing any heat exchange to take place from the working fluid to the surroundings, or we are ensuring that there will be no heat flow from the working fluid into the surroundings. So, that means delta W equal to minus H2 minus H1, that is minus dH. Change in enthalpy of the working fluid as the state changes from 1 to 2, that is the change in enthalpy. So, this is basically change in enthalpy. So, now let us use the property relation TdS equal to dH minus Vdp. We are using this relation because here it is a flow process. So, this is not a non flow system or process, because there is a continuous flow of air from one end and other end, and the sole purpose is to rise the pressure of the working fluid and also the temperature. So, TdS is equal to dH minus Vdp, and since the process is reversible adiabatic, for a reversible process you have studied in thermodynamics, this TdS is equal to del cube, right. So, for equal to dH minus Vdp. Now, the process is adiabatic. That means, so that means delta Q equal to 0. So, I should write here this is small q equal to 0. That means, we can write dH equal to Vdp. So, this is what we can write from this property relation, and we can write that del W equal to minus dH from this steady flow energy equation. So, what we can write that del W equal to minus dH equal to minus Vdp. So, what would be the work needed for the compression process, that is 1 to 2 del W equal to minus 1 to 2 Vdp. So, this is basically that we are trying to compress the air by supplying certain amount of energy in the form of work, and that energy will try to compress the working fluid, and addition of that energy will raise the pressure of the working fluid along with its temperature, and that we could express by this equation, and this is the work done. So, this much amount of work should be extracted from the turbine work output. As we have discussed in the last class, that a significant part of the work output will be consumed by the compressor itself for its operation, and hence efficiency of the gas turbine units is very small. Now, this is the expression, this is not the PDV work. Probably you have studied in thermodynamics, no matter whether the process is reversible adiabatic or reversible isothermal, work done is minus VdP for a flow process. So, work done for a flow process, whether the process is a reversible adiabatic process or the process is reversible isothermal process, work done is minus VdP. So, now this is very important to know when you will be solving numerical problems. So, work that should be supplied to compress the air, that if we assume that this is V1. So, basically that is a specific volume. If we assume that the specific volume of the air at the inlet or specific volume of the gas at the inlet is V1, then we need to compress it from P1 to P2. As I said, that in the compression process the objective is to raise the pressure with an appreciable change in density as well. So, specific volume also will change. So, that knowing the specific volume at state points 1 and 2, we can calculate what would be the work done, and that amount would be consumed by the compressor from the turbine work output. Okay. Now, question is, if we really do not know any explicit relation between specific volume and pressure, we really cannot integrate this, right. So, we need to know what would be the explicit relation between the pressure and specific volume, then only we can integrate it and we can quantify what would be the work done needed to compress the working fluid. So, now question is, there are different processes. Number 1 is reversible adiabatic compression. Process here means the compression process. So, the process can be reversible adiabatic compression, the process can be reversible isothermal compression, or it can be reversible polytropic compression. So, these three are the possibilities. The compression process can be performed assuming the process is reversible adiabatic. Compression process can be executed assuming the process is reversible isothermal, but an isothermal compression is very difficult to achieve. Though I said that there are certain applications in which that compressed gas or compressed air will be kept or stored in one cylinder or in one place, and then that high pressure gas would be used. You had seen perhaps there are many practical applications to remove dust from the from different parts of a vehicle, that mechanics or any other technical persons, he or she uses high pressure compressed air. So, that is basically compressed air is stored somewhere and that is used. So, now though isothermal compression is not of much use, but still we need to learn, and then another could be reversible polytropic compression. So, now let us first discuss about what would be the mathematical expression of work that needed for the compression, be it a process which is equal to reversible adiabatic compression, be it a process which is equal to the reversible polytropic compression, or be it a reversible isothermal compression. So, now question is, if we assume that that reversible adiabatic compression, that is PV to the power gamma equal to constant, if it is reversible polytropic compression, then PV to the power n equal to constant, or if it is reversible isothermal compression, then PV equal to constant. So, now try to understand that if it is PV to the power n equal to constant, if we replace n by this gamma, then we will be getting reversible adiabatic compression. If we assume n equal to 1, then we will be getting reversible isothermal compression. So, now let us start with this general expression, that is polytropic expression PV to the power n equal to constant, and we shall try to derive the expression of the work needed for the compression process. So, if it is PV to the power n equal to constant, or let us consider PV to the power gamma equal to constant, then this V equal to constant by P power 1 upon gamma. So, basically that, as I said you, that we can try to obtain the mathematical expression of the work done on the gas considering the generic expression PV to the power n equal to constant, but that is your homework, you can try. Today we shall try to get the expression of the work input to the compression if the compression process is reversible adiabatic one. So, PV to the power gamma equal to constant. So, you know that V equal to constant for P, constant by P power 1 by gamma, and this constant equal to P1 V1 power gamma divided by P power 1 upon gamma, or it may be P2 V2 power gamma by P power 1 upon gamma, because constant is either P1 V1 power gamma or P2 V2, because see we are considering the process is from 1 to 2, right. So, now if we consider, then W1 1 W2 2 or 1 dW or 1 W1 to 2. This is inexact differential. So, we can write either 1 W to 2, that is the work done needed for the compression of the air, and air is changing or gas is changing its state from 1 to 2. So, using either of these three. So, basically it is minus 1 to 2 this P1 V1 power gamma by P power 1 upon gamma dP. So, basically you are using this expression, that is minus 1 to 2 VdP. So, here we are writing, and V is now replaced by this one P1 V1 power gamma by P1. It is up to you, also can write P2 V2 power gamma by P, that is up to you. Now, what we can do next? You can understand that P1 is known. So, basically only the objective was to relate specific volume with P, so that we can perform this integration. So, what we can do here, P power 1 upon gamma into V1, that we can take out from this integral. So, what we can write, that 1 W to 2 equal to minus P1 power 1 upon gamma V1 1 to 2 dP by P power 1 upon gamma. So, if we perform this integration, then what we will be getting? We will be getting, you know, that minus P1 1 upon gamma V1 and then minus 1 upon gamma plus 1, that is gamma minus 1 upon gamma. So, P2 it should be gamma minus 1 upon gamma or gamma by it should be gamma minus 1 upon gamma. So, P2 power gamma minus 1 upon gamma minus P1 power gamma minus 1 upon gamma. What we can do? We can take P1 outside. So, minus P1 1 by gamma into P1 gamma minus 1 upon gamma into V1, then gamma minus 1 upon gamma into P2 by P1 power gamma minus 1 upon gamma minus 1. So, that is the expression. So, we can write one step further. So, that would be, this is P1. So, it is P1 into V1. If we go to the next slide, so W122, that is minus gamma minus 1 upon gamma P1 V1 into P2 by P1 into gamma minus 1 upon gamma minus 1. Try to understand, few minutes back we could write the pressure ratio, and what is this pressure ratio? P 2 by P1, right. If we can go back, then we can write the pressure ratio is P2 by P1. So, this pressure ratio P2 by P1, that is Rp, what we can see here, that here. So, basically if the pressure ratio is more, this negative sign indicates that work is done on the working fluid, work is done on the working fluid, right. So, basically this is the expression of the work done and it depends on the pressure ratio. If the pressure ratio is more, work done needed to be supplied to the compressor will be more, right. So, this is basically pressure or ratio work done needed to run the compressor, and that amount of work should be consumed by the compressor from the turbine itself would be more if pressure ratio is more. If pressure ratio is more, cycle efficiency will be more. So, now it is very contradicting that compressor work that would be absorbed from the turbine work output. If we absorb more work, then only if we absorb more work, then certainly the pressure ratio that would be high. So, basically these two are contradicting. I mean, if we need to get more pressure ratio, then certainly work input to the compressor will be more. In other way, if the work pressure ratio is more, then work or energy input in the form of work that should be supplied to the compressor will be more, and if it is more, then turbine work, the net work output will be less. But that means if we can increase the pressure ratio, then cycle efficiency will be maximum. If we increase this pressure ratio, then compressor work, that is the negative work, because this is the work consumed, will be more. So, these two are very contradicting. So, that is why we had to establish the optimum pressure ratio for which the cycle efficiency will be maximum. So, this is the expression of the work ratio for reversible adiabatic compression. Similarly, we can quickly write one W2 for reversible polytropic compression should be equal to minus gamma minus 1 upon gamma P1 V1. So, this should not be gamma minus 1, right. So, it should be n minus 1 upon n, right. So, this is n minus 1 upon n, right, P1 V1 into P2 by P1 power n minus 1 upon n minus 1. So, this is the expression of the work needed to run the compressor following the reversible polytropic process. Now, similarly, one W2 for reversible isothermal compression, it would be again very easy, that is minus 1 to 2 VdP. So, that is minus 1 to 2, PV is equal to constant. So, constant by constant by so this is P1 V1 by P into dP. So, that means this equal to minus P1 V1 ln P2 by P1. So, this is again this negative sign is coming, that negative sign is essentially indicates that work is done on the working fluid, because if you try to recall few minutes back, we had discussed that this is the convention. So, work that comes out from the system is taken positive, but in this case work is added to the system. So, hence this negative symbol, negative sign is coming. So, to summarize today's discussion, we have discussed about the optimum pressure ratio, which is very important to ensure that the cycle efficiency will be maximum. Then we have talked about the compressor, the need of a compressor in a gas turbine units, and then in a gas turbine unit, and then we have tried to establish the expression of the work done on the gas or on the working fluid following several processes, several realistic processes. Those are reversible adiabatic compression, reversible polytropic compression, and reversible isothermal compression. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.